My name is Matt Topp. I am a design engineer for power products at Linear Technology. I'm going to talk about the LT8710, a new, high-power, synchronous SEPIC, inverting, boost controller IC designed to drive many different types of loads. When both step-up and step-down conversion, or if a negative output is needed at high power, a non-synchronous converter may not be able to do the job because the rectification diode can get too hot. The LT8710 is a synchronous controller that can be configured in SEPIC, dual inductor inverting, and boost converter topologies. It can operate from inputs up to 80 volts and regulate outputs up to 80 volts or down to minus 80 volts. The LT8710 has 3 regulation loops. It can regulate output voltage, output current, and input voltage, and any of those can operate at the same time. The C/10 detection of the output current control is useful for charging batteries. The part can be selected to operate in discontinuous or force continuous mode at light loads. FCM at light loads produces less noise than DCM, something that only a synchronous converter can achieve. Here is a simple schematic of a non-synchronous SEPIC converter and a dual inductor inverting converter. The voltage at the anode of the Schottky goes below ground in both of these topologies, which causes difficulties in making these converters synchronous. The LT8710 solves the problem with a synchronous SEPIC and inverting converter by using a PFET switch. As shown in the SEPIC converter, the gate drive for the PFET is a positive voltage, which is simple for an IC to achieve. In the inverting converter, the gate drive for the PFET from the IC is a positive signal, but the simple cap, diode, and resistor level shifts the gate drive negative to allow the PFET to properly turn on and off. Here's an inverting converter with a regulated output voltage of minus 5 volts with a 7 amp drive capability. Using the LT8710 allows for higher current outputs than a non-synchronous inverter because the PFET will run cooler than a Schottky. This shows the efficiency nearly reaching 90% for a 12-volt input. This application shows the LT8710 charging a sealed lead-acid battery from a 5 to 36-volt input. The battery charges at 3 amps until the voltage gets close to its 14.4-volt set point. The open drain flag pin is used to set the bulk or charge voltage of the battery. Once the charging current has dropped to 1/10 its maximum, the flag pin pull-down turns off and the battery voltage will slowly drop to the float voltage. It may be desirable to charge the battery to a voltage that's inversely proportional to temperature. Using a simple resistor divider with a negative Tempco resistor, summing into the feedback node as shown with these optional components, can give a battery voltage that has a negative Tempco. Here's a supercap backup power application that utilizes all 3 modes of regulation: output voltage, output current, and input voltage. When the input voltage is present, it supplies current to the system and also charges the supercaps to 15 volts at 1 amp. When the input source is removed, the supercaps supply the current to the system and the system is regulated to 10.5 volts as set by the resistor divider connected to the input voltage sense pin. The supercaps charging and discharging scope shots are shown here. The figure on the left shows the system voltage stepping up to 12 volts. The output voltage ramps up at a rate of 1 amp. The total inductor current ramps up and settles to an average current of about 0 amps when the supercaps are settled to 15 volts. On the figure to the right, the input supply is removed and the supercaps deliver current back to the system and hold it up to 10.5 volts. In this example, the supercaps hold up the system for about 80 seconds with a 1 amp load on the system. In conclusion, the LT8710 solves a difficult design problem for making a synchronous SEPIC and inverting controller IC. This part can generate higher power outputs than non-synchronous SEPIC, inverting, and boost converters. The LT8710 is very flexible and can be used to regulate output voltage, output current, and input voltage. Visit us at linear.com for more information. Thank you.